This is podcast number 55, and today we're talking about flapping wings and how to make them more aerodynamic, so how to produce more lift compared to regular flapping wings. So flapping wings have been used on most UAVs and MAVs in general, and the reason why they use flapping wings on these particular aircraft, because it is hard to do, is because you can have potentially more lift production if you do it properly. And flapping wings are inspired, obviously, from birds. Now, this paper that we're looking at, called Check Valve Design and Enhancing Aerodynamic Performance of Flapping Wings, is interesting because it aims to kind of mimic how birds fly. So, in terms of flapping wings in general that have been implemented to date, they're not exactly the same way that birds fly. So, in podcast number 6, which is called Birds Are Liars, I go through how birds actually fly, and it's not the same as what people generally think. And if you want to learn more about how the exact mechanisms behind flight, check out that podcast. This paper and this podcast follows on from that effectively, just 49 podcasts later. And we talk about how to actually design a wing to kind of mimic this flow physics and why it's different to regular flapping wings that we use to date. So this is open access, so you can find it in the link in the description. And as mentioned in the title, it says check valve design. So let's talk about what this means. Let's scroll down to a picture with what they have. So let's say you have this picture here, which is just two wings flapping. And on the wings, you have on each wing you have a valve, and this valve can open on the upstroke and closes on the downstroke. And the reason why this is important is because on the upstroke, if the wing is going tracing the exact same path on the upstroke as a downstroke, just in opposite direction, you're covering the exact same area, the exact same volume, and the wing, if it's flat, is going to be producing the exact same amount of force just in the opposite direction. So technically, you won't actually get any lift at all if it's a exact carbon copy of the downstroke just in the opposite direction. So the net lift will be zero overall. There are other ways around that they've looked into, but this check valve is one way that this paper is looking into, and we'll get into why this is important. So they start off saying that the Delphi Nimble and the KU Beetle are two successful examples that perform hovering flight and some cool maneuvers. However, based on the flapping wing design improvement by the conventional wind tunnel testing, the forward flight and level cruise of flapping wing MAVs are still the most primary forms of flapping flight under investigation. However, to reduce the air drag and flight power during cruise, so as to achieve long-term flight endurance, it's critical to further develop these flapping wing MAVs. So in other words, what they're saying is these current methods of flapping flight, they work to some extent, but they're not that good. Whereas if you can mimic a bird more, then you can get more efficiency out of that. So there are several ways to improve lift, for example, by increasing the wing foil thickness and the camber. So that means that the upstroke is not going to be the same as the downstroke, and you can get a net overall lift as opposed to no lift. You can also improve the lift production through adding wing corrugation. That's pretty cool. Enlarging the stroke angle using wing rotation mechanisms, so the wing rotates and it follows a different path on the upstroke to downstroke. Using morphing wings, so on the upstroke the wing is actually a different shape to on the downstroke, which then changes the amount of lift that it produces and can be less lift. So the net result is an increase in lift. And also by changing the wing materials or by adjusting the wing stiffness along the chord-wise or span-wise directions. But not many studies have been performed to enhance lift through mimicking feathers in the upstroke. So again, in podcast 6, I go through this in detail, and it's really interesting how birds actually fly, so check that one out. But just briefly here, the way that a bird flies is that on the downstroke, there's a lot more to it than this, but just briefly on the downstroke, the feathers all clamp together, and that provides one surface, this one complete surface that produces lift. On the upstroke, though, in certain regions of the wing, the feathers actually get turned perpendicular, so that on the upstroke, the air goes through the feathers, like between the feathers, and it's not producing lift now. So the overall effect is a net lift. And this is what these valves are trying to mimic. So they have a graph here, which is on the downstroke, the valves are staying closed, and on the upstroke they open, and the effects on the lift production is, so on the downstroke you get obviously a positive lift production, but on the upstroke, if you don't have any valves, then it means that you're producing negative lift, and overall the amount of lift that you produce is not really that much. But if you can implement these valves, which effectively act like these feathers that are turning perpendicular so the flow can go through the wing effectively, then you're not producing as much lift. And their general concept of this is that if you do this with a valve, then you can really cut off how much negative lift that is being produced on the upstroke, and overall the MAV that you have can then fly much easier. You don't have to produce nearly as much lift over the entire cycle to remain in the air. So the hovering and general cruising flights are much more efficient as a takeoff and pretty much every maneuver. So that's the idea behind the valve. They want to make it mimic the feathers of a bird. Now, there are other flow physics that I should mention. I'm not going to mention the flow physics here, that's in podcast 6. There are other flow physics that this valve will not mimic from compared to a bird. This is one major step in the right direction in terms of the upstroke general idea. So say that the valve opening action can effectively reduce the magnitude of the negative lift, since its pinhole opening spoils both the completeness of the wing and the smoothness of the airflow. On the other hand, it also shows that the closing of the check valve during the downstroke completely restores the wing contour. So in other words, on the downstroke, the wing hopefully won't be affected by the check valve, but on the upstroke, it is very beneficial. However, there are certain problems that occur with this check valve, and some of them are knowledge-based. So problem 1 is there seems to be no baseline for the size and number of the 4 serpentine S-arms that connect the check valves. So number 4 is not a prime number, thus resonance may be present in this design. So let's quickly just talk about these check valve things, this serpentine design. So the valve is connected to the outside, so the inside part is connected to the outside through these just little arms. They're called serpentine arms, so just an S shape. And how many of these arms should you have? And the reason why they're interested in this is they can potentially produce resonance. And so the number of these arms could be detrimental to the performance. So they want to investigate that. Problem 2 is that other studies failed to describe the dynamic behavior of the check valves. Therefore, it is difficult to justify the appropriateness of the design. And problem 3, there are too many check valves distributed at the leading and trailing edge of the flapping wing. They will induce many optical issues. As we'll find later, that more is not necessarily better here. To eliminate these stumbling blocks or these 3 problems, a modified design and corresponding experimental studies are conducted. And in this work, the check valve is designed by examining static and dynamic characteristics using FEA. And wind tunnel experiments are conducted by incorporating the check valves in the flapping wings, and the aerodynamic performance characteristics are measured. So let's talk about the check valve design first. They say that the inspiration of the check valve design comes from observing the functionality of the feathers in ornithology, so in bird flight, and how they are used to reduce the negative lift through the ventilation mechanism. The deformation of the check valve during flapping is considered to be a dynamic problem, and determining the transient solution is laborious. So what they're saying is that to look at the dynamic effects of the check valve during flight, it's quite difficult. So they're just going to look at the static solution and kind of assume that the dynamic solution is somewhat similar, is indicative from the static solution. So they just have these pictures of these S valves. They're typically what you would expect. There's an outside disc, and then there's an inside little disc. And the inside disc is connected to the outside disc with these arms, and that moves up and down to open and close the opening, depending on the force on the disc. Now, they did an FEA analysis on these little arms to see if they would snap, so they made them out of PET, so polyethylene tetraphthalate, I think it's called, and the tensile strength of PET is 55 megapascals. And in their FEA analysis, the stress on these little arms are nowhere near that. That's like 2.3 megapascals. Now, interestingly, I'm not sure whether the cyclical loading of them, so the fatigue of them, will make them break over time. But potentially that is a possibility. So how do they integrate these check valves into the wings? They say the integration of several check valves on the leading and trailing edges of the wing membrane introduces unpredictable aerodynamic phenomena. The arrangement of a single pair of check valves is modified based on the observation of high-speed photography and the instantaneous position of the central disc cap, which is shown in Figure 5. So they put these, let's go to Figure 5. They put these valves on these wings, clear wings, and then they shot the motion in high-speed camera, and then they looked at how the valves were behaving. Now, from these pictures, I can't see anything because everything's clear, but somehow they managed to figure out the deflection of these valves, and they came up with a decent idea as to where to put them and how stiff to make everything, etc. But in Figure 4, they have two main designs. They have one design which is just you have one big check valve on each side, so on one wing and on the other wing. The other design is you have a bunch of check valves, so you have 6 on each side, and they're effectively around the wing tips. And you might, like, I would have thought that a lot of the check valves would be probably more beneficial because they would act more like wings. In fact, if you look at podcast number 6, we talk about how the feathers rotate. It's mainly the wings on the outside of it's mainly the feathers on the outside of the wings that rotate to reduce the negative lift. So putting these check valves here, they kind of mimic more of the bird, but are they good or not? We'll find out. These two big ones, they're kind of just like you put two big valves, just smack bang in the middle, and see how it goes. So it seems like it's not as good a design, but we'll find out later. So they the way that they make the wings flap is through just a DC motor disconnected, and it goes around and around, and they go up and down. Now, the single pair of valves, they have a 7.43 millimeter disc cap, whereas the multiple valves, so the 12 valves in total, they have 4.95 millimeter disc cap. So in other words, if you look at the entire surface area that these valves are taking up, the three individual ones, they're only taking up like not even 10% of the area that the other 12 are taking up. But the drawback of a multiple check valve design, so the one with 12, is that it weighs more than the single pair check valve, and it worsens the lift enhancement, which can lower the effective lift value. So in other words, we might think having all these valves near the wing tip, which mimics a bird more, would be beneficial, but they add weight and then they also spoil the lift, probably because they're not flush with the surface. So unlike feathers, which are designed to really clamp together and provide a fairly nice surface, these valves, they're going to have they're going to protrude up into the air a little bit, and that's going to potentially spoil the lift. Whereas having two bigger ones, they don't do that as much. Now, in terms of their validation of this idea, they did some wind tunnel experiments. And in the wind tunnel, which is shown in Figure 6, the wind tunnel had a contraction ratio of 6.25. That's okay. The higher the contraction ratio, the lower the density typically, and the straighter the flow. And the test section is 30 centimeters by 30 centimeters by 100 centimeters. And the following test conditions were investigated. So the wind speed between 0.5 meters per second and 3 meters per second, and then various driving voltages, which changed the flapping, and then inclined angle of the MAV from 20 degrees to 70 degrees. So the wings are flapping at different angles, and the actual like the fuselage part of the MAV, it's like the body of the bird kind of thing, is angled from 20 degrees to 70 degrees. And interestingly, now they have graphs showing the lift production of this MAV with and without the check valves at different voltages. So the different voltages, they just change the lift force. And on the left side, there are the lift productions without valves. On the right side, it's with valves. And it's very easy to see that without the valves, there is a lot of negative lift being produced, as much as there is positive lift almost, maybe even more. On the other side, where you have the check valves, the negative lift is pretty much cut out completely. So these valves have now completely reduced the negative lift. So the bird, the MAV, is producing only positive lift, it seems now. So these valves are working very well. And then they also have the lift force integration and with and without the valves, and the net thrust force. So the thrust is obviously important for like moving forward. Now, without the valves, you can see that as the wind speed increases, the lift being produced increases really with every angle of attack. However, interestingly, the thrust reduces linearly effectively with every angle of attack as the wind speed increases. Alternatively, when you put valves onto these MAVs, the thrust, first of all, is greatly affected in that it becomes pretty much stable. So really now it's not really increasing or decreasing as the wind speed increases. It's more just fairly flat overall. There are obviously some conditions where the thrust increases or decreases depending on the wind speed, but overall it's fairly flat. So in other words, it provides a much more stable flight for this MAV because you don't have a reduction in the thrust production. Now, the lift production is significantly greater for the MAV when you have a check valve. That's because you knock off that negative lift during the upstroke. So it's very beneficial for all wind speeds at all flapping conditions and angles of attack. So before we go any further, I just want to mention, if you want to make your experiments better, you need to measure the density of air. So in podcast number 54, I go through a couple of case studies on how the density of air changing that, which changes on a regular day about 2 to 4%, affects your results. For example, the von Kallmann off of a bluff body or the lift off of an airfoil, and how they change your lift and drag results, the frequency sheddings, the stall patterns, everything. And this is a typical effect of the change in density, and that happens on a regular day that most people don't measure the density. So you need to measure the density to get rid of that error. If you don't, then you have a massive error in your experiments that you don't even know about. We make the Atmosphere Hawk, which actually measures the density for you and prints it on a nice big screen for you, so you can see it anywhere on your wind tunnel. And you can factor that into your experiments. If you don't do it during your experiments, you can't correct for it later because the flow physics is wrong. So in other words, your experiments are now corrupt with this error. So you need to get rid of it during your experiments. Otherwise, it'll be with you forever. So make sure to get the Atmosphere Hawk, link in the description. So getting back to this paper, they say that for the case of 1.6 meters per second and a 30-degree flap angle, the check valve case generates 14 grams force lift. So in other words, like 1.14 newtons, which is 27% higher than the 11-gram force lift of the membrane wing without the check valve. And in addition, with the case of 1.75 meters per second flow and a 30-degree angle attack, the check valve case generates 17 gram force lift, which is 68% higher than the 10.1 gram force lift for the membrane wing without check valves. So in other words, adding these check valves dramatically increases lift anywhere between 30% and 70%. And it might even be more at different angles of attack and different flow speeds and different flapping motions. So all around, these check valves are very beneficial. And I have pictures here showing, this is CFD now, showing how the flow moves around the wing with and without check valves. On a downstroke, so the check valve is closed, the wing acts very much like a regular wing where you have quite a big wake and you have vortices rolling up and everything. I'm not going to go into that here. Podcast number 6, check that out. That's where we go into it. Then on the upstroke, if the bird or the MAV is going straight up, so the flapping in a typical angle, the check valve opens and then obviously bleeds air into this wake region. And the wake is far smaller. Like it's like probably 20% of the wake compared to the downstroke. So in other words, the wing now is not really disturbing the flow nearly as much as on the downstroke, which is why you don't get as much lift being produced. Now, in hovering flight, for example, like a hummingbird, where the wings go, back and forth a little bit, so the wing is now perpendicular to the ground. The wake is still reduced dramatically, but it's a bit bigger now, and the flow goes through the check valve and helps reduce the amount of lift on the stroke where the valve is open. They say that the small size of the check valve may not be suitable for smaller flapping wings, so that's one possibility. You may need to just have, I guess, even smaller check valves. I don't know. I imagine you could just get a small check valve and it would still give a similar sort of result. They say that this is interesting. They had a good idea. They said the valve disc cap is attached upside down, So the assistance of gravity helps to open the valve. So that's a good idea. You use gravity to open it instead of just the force of the air. And that means that it's more robust that way. And you don't need to have as stiff arms, I guess. And it works potentially quicker. And then they have some conceptions of how the flow moves around these wings. So they have just a nice little drawing here. On the downstroke, the valve closes, obviously. The air goes around. Interestingly, they say that there's a leading edge vortex which comes from the wing, which is true. It comes from, look at podcast number 6 again. And then that still is intact behind the wing. As soon as the valve opens, though, on the upstroke, this leading edge vortex is no longer present. I guess it's been effectively destroyed, or even maybe didn't even exist to begin with. And now that lift being produced from that leading edge vortex is no longer there, which is one of the major reasons why probably that on the upstroke, the lift isn't being produced as much anymore. The leading edge vortex has changed. It's no longer there. The flow physics has changed, so the lift production has dramatically dropped. So not only has effectively the area that this wing sweeps over a little bit smaller, the flow physics is completely different and for multiple reasons. So they then go on and say that they tested this MAV in a real-time flight test. It was observed that the flapping wing MAV with check valves makes a sudden Immelmann turn after takeoff and generates a high lift value. Immelmann turns. Immelmann was always doing these turns, and unfortunately, this MAV is doing the same thing. And that happens because the lift being produced is much higher than the weight of the body that's flying, and that means it just goes up like it goes in a loop upwards because there's so much lift, and then that makes it loop back down because it loses lift as it goes higher because it's a very high angle of attack, and then it just loops down into the ground. And that's what this MAV does. But because it produces so much lift now, they say it could potentially be better for carrying higher payloads or greater payloads or more batteries. So then you can fly further and take more stuff. Alternatively, you can just decrease the voltage that you're running this MAV at, so you're not flapping as hard, and then you can fly further anyway. So in other words, this is a very successful design in that you've produced so much lift now that when it's so light, you can't actually fly because it just produces so much lift. It does these Immelmann turns, and it needs more weight just to remain in steady flight. So that's interesting. So in conclusion, they say during the best cruising conditions, the flapping wing with check valves generated 27 to 68% more lift than the membrane wing without check valves. And a higher lift maneuver was also performed due to the large lift enhancement by the check valves. In summary, the results of this study show that the lift enhancement through the incorporation of check valves is effective for bird-like MAVs with a wingspan of about 20 centimeters rather than insect MAVs. So as I mentioned earlier, these valves may be too big for like the micro MAVs, but who knows, maybe not. So that's in this podcast. Make sure to like and subscribe, and check out the Embassy of Hawk to make your experiments better. Peace out, amigos.